In this example, we're going to find the equation of a tangent line to the parabola f of x equals x squared at the point 1, 1. And to do that, they want us to use this definition right here, which states the slope is equal to the limit as x goes to a of f of x minus f of a all over x minus a. So let me show you what that means. Okay, here we have the parabola f of x equals x squared, and we have the point 1, 1. Okay, and what they want us to do is they want us to find the equation of this tangent line through that point. Okay, to find the equation of a line, we need a point, which we have, and we need a slope. Well, normally to find the slope, we need 2 points, right? Okay, so let me go ahead and put another point on the parabola. Okay, there's a little problem with how I have this labeled. Okay, x comma f of x could be anywhere on the plane. So let's try to fix that. Okay, let's go to this. Okay, to be on the parabola, notice that it's defined, the function is defined to be x squared. F of x equals x squared. So maybe I can make a little substitution right there. What happens if I do that? Well, that guarantees that this variable point is on the parabola. Okay, I have a few of these labeled here, but actually there's infinite of these points on the parabola. Okay, so let's just focus on when the point is located here. Okay, so now if I connect those two, I have what's called a secant line, and I can find the slope of that secant line. There's a little problem right now though, because the slope of that secant line is not even close to the slope of our tangent line. But remember, this point right here can be anywhere on the parabola. What if it's closer to the point 1, 1? Okay, let's take a look at what happens if I move this variable point closer to the point 1, 1. Okay, you can see that as that point gets closer and closer to the point 1, 1, that the slope of my secant line gets very, very close to the slope of my tangent line. Okay, through limits, that variable point will never actually arrive at the fixed point, but it will get infinitely close. So hopefully it stands to reason that if the variable point becomes infinitely close to the fixed point, that the slope of the secant line will become infinitely close to the tangent line. Okay, so let's take a look at the problem again. So now note that we have the fixed point 1, 1, and we have this variable point x comma x squared. So I can find the slope between those 2 points. Change in y would be x squared minus 1, and the change in x would be x minus 1, rise over run. Okay, now this right here, this limit, as x approaches, okay, so what do I want to do here? I want this x right here to get very infinitely close to 1 right here. So I want that. Okay, so normally what we do with limits is we go ahead and make a substitution. Let's put 1 in right here. 1 squared is 1, minus 1 is 0 on top. And then 1 right here, 1 minus 1 is 0. So this is indeterminate. That normally tells us we have a little bit of work to do. So let's take a look at what we have here. Okay, looking at this limit, we can see that the top right here is the difference of 2 squares, which means we can factor that. So let's go ahead and try factoring that. So the top factors to x plus 1 and x minus 1. And the bottom remains x minus 1. Okay? Well, those will cancel. Now let's try our limit again. Limit as x goes to 1. Okay, now when I substitute 1 in this time, 1 plus 1 is 2. So according to this definition, the slope of this tangent line right here is 2. Well, let's see if that makes sense. So from here to here's another point on the line. Looks like I go up 2 over 1. So it seems very reasonable. Okay, now we have a point and we have a slope. So now we can write the equation of the tangent line in point-slope form. So I'm going to go y minus 1 equals x minus 1 with our slope right in front. That is the equation of our tangent line in point-slope form. They didn't ask us to write it in another form, so this is sufficient.